Good evening. It is 7 p.m., but nobody has yet joined, so we will wait for a couple of more minutes before we start. Thank you. Good evening and welcome to week 12 of the live sessions for Fundamentals of Additive Manufacturing Technologies. I am Sourav Goswami, a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. I work broadly in the area of additive manufacturing. As usual, our agenda would first include recapitulation of the contents that were covered this week, and then we'll move on to solve some uh, illustrative problems that will help us clear our concepts as well as help us solve the assignments for this week. So this week was primarily devoted to powder bed based processes, namely electron beam based powder bed additive manufacturing and binder jet based or binder based powder bed additive manufacturing. We have already covered electron beam based powder bed additive manufacturing last week, and so we'll start with the binder based AM process. Broadly, the contents that were covered include the working principle in the subsystems, the various powder and ink materials that can be used, types of scanning system, the powder delivery system, some of the examples of the machines, as well as some a very interesting AM application which most of us might not be aware of, which is in the pharmaceutical industry in time delivery drugs. This is the classification chart that we have been following for powder additive manufacturing. We already covered the powder feed additive manufacturing. An example of such a process can be directed energy deposition using a laser. And among the powder bed additive manufacturing technologies, we have already looked at the energy beam based powder bed additive manufacturing technologies, among which first we looked at the laser beam based technology, such as SLS, selective laser sintering, or SLM, selective laser melting. Last week, we also looked at the electron beam based powder bed additive manufacturing, sometimes also called as electron beam melting, where the energy source is an array of electron beams instead of a laser. As discussed, we have covered SLS and SLM. And this week, we'll be looking at the binder based powder bed additive manufacturing, also commonly known as binder jetting. So here is the subsystem level classification for the binder bed powder bed AM processes, as well as a schematic. So this schematic is similar to other powder bed based processes where there is a reservoir of powder and which feeds the powder to the recoating system. Now this feeding motion can either be a top feeder or a bottom feeder. The schematic here shows a bottom feeder where there will be an upward movement of this stage right here, which pushes a predefined layer of powder up for the recoater, which again may be a blade, also called a doctor's blade, or in the form of a roller, or it can also be in the form of a simple slot feeder, which then transfers this pre-decided uh, height of powder or the fixed volume of powder onto the printing area. Now the printing area will have a cavity on top generated by a downward motion of this stage right here, on top of which is the substrate or the build plate. And in that cavity, the recoater or the roller will deliver the predefined amount of powder. And again, if we are using, say, a roller, it may also lead to some further actions such as the better flowability or the compaction. We'll look into those aspects. Here, the deposition is actually accomplished by this ink head that we see. And this ink head has several tiny nozzles, as you can see right here. There are several of them, which selectively deposit or drop this ink or binder onto the powder bed. And wherever this ink or binder will get dropped is the region where the powders will get, say, diffused together, and that will where the parts will be printed in each layer, and the rest of the powder will remain as loose powder, which can be separated later. Again, the loose powder itself acts as the support structures to support any overhanging features or to support the part in general, and no explicit support structures are required. So the joining mechanism is via binder only. Among the powder materials, all sorts of materials can be used, such as say ceramics or metals or even multi-materials. The scanning system is the ink head, which moves over the printing area and deposits the binder or ink only in the regions where the parts has been printed. Powder delivery system, as we discussed, can either be a top feeding or a bottom feeding type. The recoating system, again, just like other powder bed based processes, can be of a blade type, such as using a doctor's blade, or it can have a roller, which can again have either a forward rotating or a counter rotating motion, or it can be a simple slot feeder. The build atmosphere for these binder based powder bed AM processes is usually open atmosphere. There is no atmospheric control that we exercise, and that pressures are atmospheric. There is no vacuum either. So here are the various categories of each subsystem. So in terms of the powder and ink material, we can process ceramics, polymers, metals, and also a combination of these into a multi-material. So right at the outset, we can see that in terms of the processing capability, the binder-based powder bed AM techniques are simply unmatched because there is no single process which is so versatile in terms of the powder materials or the feedstock materials which it can process. And the reason for this is because it does not really involve any melting or any fusion or of the powder particles. So say if you have a machine or a technology which is suited for metals, it might not be suitable for ceramics because they might need, say, the energy source or laser of a different wavelength. Similarly, if you have a machine suited only for polymers, the temperatures which it can achieve will simply not be enough to melt metals. But in the case of binder-based powder bed AM, all of these difficulties are sidestepped and it can process all of these materials equally well. Also, it can process a combination of these materials. The scanning system can will be the ink head using either a single nozzle or a multi-nozzle. So single nozzle technology is here given just for the sake of completeness, but most commercial systems would be using a multi-nozzle setup because a single nozzle setup will simply not be, say, economical to use or simply impractical. The powder delivery system, as we discussed, can either be a top feeding type, where the powder is delivered from the top in front of the recoater or the roller, and then the recoater moves the powder over the printing area, and we have top feeding hoppers on both sides. Or it can simply be a bottom feeding type, where we have a reservoir of powder, which moves up by a fixed layer height each time, and then that layer of powder is carried over by the recoater or the roller onto the print area. The powder recording system, again, just like other powder bed based processes, can either be a blade type, a roller type, or the simplest being a slot feeder. As we have been discussing, so a wide choice of powder and binder materials and their combinations are possible. The binder can also be mixed with other materials. So in binder based powder bed AM processes, it is possible that 30 to 50% of build material can come with the binder. It's not necessary that whatever structural material or build material we are willing to print has to be in the powder bed from the very beginning because that might be problematic. We might not really be able to control the distribution of local distribution of powders and their compositions within the bed. But what we can do is we can also selectively drop those materials along with the binder. And the extent of this powder that can be or structural material that can be deposited with the binder is between 30 to 50%. So quite a lot. And the remaining 50 to 70% can actually be in the powder bed itself. Again, the different color or property materials can be dispensed by different print heads. This gives us a lot of versatility for printing, say, finely graded materials or FGMs. Again, the binder-based powder bed AM can exercise control over the local material composition. The material can be in the liquid carrier or also in a molten state. And the proper placement of drops can be used to create surfaces of controlled texture and to control the internal microstructure of the printed part. Now, the technique definitely has some unique flexibility, and parts of any complex geometry can be created and out of any material of our choice, including most engineering materials such as ceramics, metals, polymers, and a mixture of those to produce a composite. Again, the local control can be exercised to control the material composition, density, microstructure, color, and even texture to give us FGMs. Again, it is also very readily scalable in production rates, and thus it can have good industrial adaptability in coming time. We know that some of the AM processes, while they are very accurate and they have a very good geometric tolerance, they are too slow or simply too expensive to be scaled up to industrial demands. But binder-based powder bed AM is one of those technologies which truly has the potential to reach or to match the economics of an industrial scale demand. And this can be achieved through the use of multiple nozzles, which have been already commercially developed. Now, depending on the structural material that we are using, the ink that or the binder that goes with it will also change. So, if we have the binding component in the ink itself, in such cases, the inks would either be an inorganic or organic type, and the powders which can be processed via this route are ceramics, metals, and polymers. So, this covers all of your engineering materials. Whereas, if there arises a case where the binding component is also present in the powder itself, and the binder or ink that you are dropping just acting as an activator or simply activating the process of say bonding. In such cases, the inks can either be aqueous or of a solvent kind, and the powders which can be processed can be say starch or cellulose or even plaster of Paris, as well as some cements. As we have been discussing, no commercial system possibly uses a single nozzle for depositing the ink or binder onto the material. But to understand the working principles of the multi-nozzle system, it is best to start with a single nozzle and then we can simply scale or extrapolate the analogy that we derive. And so, even in terms of the feeding, the droplet supply of droplet can either be in a continuous fashion or it can be in a drop on demand fashion. In continuous fashion, as the plot tells us, so this can be say the time axis, and the drop ejection signal is given periodically and it does not stop. So it continues giving the drop ejection signal. So drops keep coming out of the nozzle. However, when the laser head when the deposition head is actually moving over areas where we do not want to deposit the binder or which we do not want to print, this ink still continues to be deposited or to be dispensed from the nozzle. However, it is not allowed to fall onto the powder bed and it is pulled into this cup-like structure by using some electrostatic charge. So at the time of uh, dispensing this ink from the nozzle, an electric charge is supplied to it, and the opposite charge can be activated here, such that when we do not want the ink to fall onto the powder bed, we can activate this electromagnetic field, and this electrically charged ink, say if it has a negative charge, it can get attracted towards this cup, thereby ensuring that the binder is deposited only in the desirable regions. Whereas in the more modern or say more accurate drop on demand systems, we are giving the drop ejection signals only when needed. So say this signal can correspond to this drop here, whereas this one can correspond to drop 2, and in between, no material comes out of the nozzle. And this is especially advantageous because as we can see in the first case of continuous dispensation of the binder ink, there would be a lot of wastage. And even if some way can be figured out to reuse this binder material, it is expected that that will involve at least certain post-processing. So yeah, not very economically sound, as well as the quality and the properties of the ink might change because of its interaction, as well as its charging and discharging. So the drop-on-demand technology is preferable. And even in terms of the dispensing system, so the nozzles can be of two types. They can either be operating on a thermal mechanism where we there can be say a resistive element which can be heated, and when we apply a voltage to it, its temperature rises. which leads to the formation of a vapor bubble. This vapor bubble then pushes out a certain volume of liquid out of the nozzle and onto the print bed. Again, the other mechanism can be a piezoelectric mechanism, where when we apply voltage to some piezoelectric material, it induces some stress-based deformation. Because of the deformation, the volume surrounding it would be affected, and that would lead to the ejection of a given volume of binder ink from the nozzle. We also have a comparative table here which shows the advantages and disadvantages of these two technologies. So a thermal head will have a lower cost and a higher printing speed. However, this will also risk exposing the binder material to higher temperatures, which is not desirable because it will affect the reusability of the ink, as well as binder jetting. The perhaps one of the major advantages of binder jetting is that it operates mostly at room temperature. I mean, the post processing would definitely involve higher temperatures, but the printing process itself operates or is performed at the room temperatures only. And because of these low temperatures, there is no presence of residual stresses as well as the need for high energy inputs. So we would want to preserve this advantage to the extent possible. And this is done through the piezoelectric head, where there is zero to or no thermal exposure of the binder ink. Again, for thermal based nozzles, the droplet size might be non-uniform, whereas in the piezoelectric nozzles, it is thoroughly uniform and mostly controlled. And in the thermal head, even the directionality of the droplet is not consistent, whereas in piezoelectric head, the droplet will mostly fall right where it is intended. So in this case, we can want the drop to fall normally or perpendicularly right where the nozzle is situated. So for piezoelectric head, this accuracy is maintained, whereas for thermal heads, it might not be the case. As we have been discussing, the powder feeding mechanism can either be a bottom feeding or a top feeding. So for a top feeding, say we can have a hopper which is full of powder particles, and we fill this up at the start. And for each recoating cycle, it will deposit a requisite amount of powder in front of the recoater, and the recoater will then deliver this powder as well as say compact it into the required layer thickness over the build platform. The recoating system again is similar to what we looked at during our investigation of the electron beam based auto by AM machine technologies. So it can either be a Dr. blade, which is just a say a prismatic or a flat blade of metal, ceramic or silicon, which moves the powder particles over the intended area, or it can be a roller type, and based on the motion of the roller, say if it is moving along this forward direction, then the direction of rotation of the roller will determine whether it is a forward rotating or a counter rotating roller. Each have their own advantages. The forward rotating roller would compact the layer of powder and lead to better part density, whereas the counter rotating roller will actually increase the powder flowability. So in case you have powders which are not very highly spherical or where the distribution of powder sizes is wide, we may use a counter rotating roller. However, using the forward rotating roller is more important because here the there is no fusion involved and no melting involved. So the compaction of the green part or the density of the green part will indeed decide the density of the final part itself, even though we infiltrate it with a secondary metal. But in terms of the primary build material, the density of the part will somehow be decided in this preliminary step only. So the more compacted the powder layer is, the more density the part can be expected to have. Of course, some of the earlier machines and even some of the most commonly used machines use the simplest feeding mechanism, which is just a slot feeder. So here we see the hopper or the reservoir full of powder, and by the rectilinear motion of the hopper, the powder is deposited over the necessary region. And in a way, it can be seen that this flat back wall of the slot feeder itself is acting like a doctor blade to move the powder along. So let us check out some of the machines which have been built and which operate on the principles of binder-based powder bed AM. So one of the very first machines, which was developed by MIT, could process ceramic, polymer, and metals as well as a combination of these using a multi-nozzle deposition head and a top-feeding powder delivery system utilizing a slot feeder. And it was called Z-Corp's 3D printer. The terminology 3D printing itself has been developed by MIT, and it is in a way quite similar to selective laser sintering, except instead of using the fusion mechanism and using a laser as the energy source, here we use a binder liquid which is sprayed in selected regions, and the raw material is of course powder. It was initially used for rapidly generating prototypes, but later it was used for generating full parts, structural parts. And the green parts, however, will require post-processing in the terms of sintering inside another furnace at higher temperatures. The working principle is that upon spraying the binder through nozzles onto the selected region, the particles in that region stick together, and the remaining particles which remain loose will then act as the uh, support structure or will provide support to any overhanging features that might exist in the part. The binder spray makes use of mechanical movement. However, there are multiple jets and the process can be pretty fast. Explicit support structures are not required because firstly, the loose powder particles themselves are acting as support structures. And secondly, there are no thermal stresses involved here or no residual stresses involved, such as was the case in powder bed AM. And therefore, there is a very low probability of warping of the parts. Since there is no warping, we don't even need the support structures to restrain the part in place. And as discussed, a very wide variety of powders and almost all the engineering materials can be processed by this route. Alternatively, it has also been called by the names inkjet 3D printing, Z printing, or simply 3D printing. This had been developed by Z Corp, which is an American company, and some of the specifications are also given here. So it can have a resolution of 300 into 450 dpi. So this dots per inch is the resolution which is also specified for our 2D printers. So we can see that indeed it was just a technology scaled up to the Z axis, but has its origins in the usual 2D printing which you all encounter every day. It can process very minimum small features to the extent of 0.4 mm, which is a really fine step size or layer height. The build speeds can be up to 0.8 inch per hour in the vertical build direction. And initially the build size was of the order of some 236 into 185 into 127 millimeter cube. Initially, it worked with stars and plaster formulations. Of course, later all the other materials could also be processed. Another one, which is the sand printing machine by X1, uses the ceramic powder as a feedstock. Again, uses a multi-nozzle deposition head and a top feeding powder delivery system delivered through a slot feeder. The metal printing machine by X1 uses the metal powder as feedstock instead of ceramic, and similar to other technologies, uses a multi-nozzle deposition head and a top feeding configuration to deliver the powders via a slot feeder. And now we will look at one of the very interesting examples of binder-based powder bed AM, which I came across, which is the time delivery of drugs. And this is also a very strategic application because pharmaceuticals is one of the key industries which will always be required and which needs rapid development to ensure human wellness and prolong human health. And it is very interesting to find that a manufacturing process, which is originally envisioned for, say, engineering materials such as metals and polymers, actually finds its way into a highly quality controlled and highly sensitive application such as drug manufacturing. So binder-based powder bed AM has been found to be very suitable for producing time delivery drugs. And this is because this is perhaps the only process that dispenses materials from two different sources. So as we discussed, it's not just in the powder bed where you can have the structural material, but material can also be dispensed along with the ink or the binder. Some 30 to 50% of the material can be dispensed in the ink, and the remaining 50 to 70% can be held in the powder bed to begin with. And the company Therix from USA is the pharmaceutical company which actually produces the drugs in this fashion. However, in principle at least, so any deposition process with an ability to control flow rate of materials can be used. We know that for drugs, actually the rate of dissolving or the rate of dissolution is proportional to the surface area of the tablet. So the concentration of the drug shall be distributed such that I think the plot is available in the next set of slides. Yeah, so let us resume from here. Here we also have the plots for the time delivery of drugs. And it also shows the production line. So here you have the powder getting dispensed from the top. This is the powder, not the binder, please be sure. And this gauntlet is continuously moving. And here we have a roller. So the roller will compact as well as evenly spread the powder along the gauntlet. And here, some distance down the production line, we have the binder jetting head, which is selectively depositing or dropping the binder in the desirable region, which you see as the blue and purple dots here, which leads to the production of drugs. So maybe each of these small pellets may form just one single layer, and many such layers can be again compacted together to form one tablet. And as we have been discussing, the binder-based powder bed AM is a suitable process for producing time-delivery drugs. And this is because it dispenses materials from two different sources, as we see here. Now, the tablets of various APIs. So actually, API stands for active pharmaceutical ingredient. Tablets of various active pharmaceutical ingredients with different shapes and release profiles. So this release profile basically suggests at what rate the tablet is dissolving with time into the human body, and of course with dissolution at what rates it is delivering the or releasing the drugs into the human body. And such have been developed by using binder jetting. There are certain FDA approved forms as well, such as Spritam, which was developed by the zip dose technology of Theriform. Yes. Here we have the drug release plot versus time. So the rate of dissolution of such a drug or a tablet is actually proportional to the surface area. Because a drug gets diffused across the surface, the concentration of the drug should thus be distributed in such a way that the specified or fixed constant rate of drug is proportional to the conformal area. Because as we know, initially the surface area is high, and so the amount of drug that is released would also be high. But with time, the surface area keeps getting reduced as the tablet itself is dissolving. And since the drug release rate is simply proportional to the surface area, when the tablet gets smaller and smaller, the extent of drug release also gets lower. This is shown in the blue curve here, where initially you have a very good slope or a very steep slope of drug delivery, but with time, this flats out and eventually reaches zero. However, what is more preferable is actually a linear release profile or a sustained release. So this is usually called sustained release, where you actually have a constant rate of release of the drug with time, and this which can be more effective in solving a human ailment. So this can actually be accomplished by varying the concentration of the drug which is shown here by the intensity of the yellow color. We see that here perhaps it is the darkest, then somewhat lighter here. So I'm drawing maybe some iso contours in terms of colors, and in the outermost regions, it is the lightest. And this color code can actually correspond to the concentration of the drug. So when you have a very large surface area, the concentration is somewhat low, such that the product gives you a constant drug release. And as the surface area keeps decreasing, we keep increasing the concentration of the drug, so that the product of the smaller surface area and the higher drug concentration is still constant and equal to the initial rate of drug delivery. Thus, in a way, this is a functionally graded material because we are radially varying the drug concentration. The concentration is decreasing as we are moving away from the center, and such degree of control can be exercised via this binder-based powder bed AM process. Thus, the concentration at conformal layers in closed intervals is decided and controlled. The resulting gradient geometry again is sliced into horizontal layers, retaining the information of the relative concentration. So, as we discussed, when we are actually printing this by binder jetting, we will maybe deposit the drug into these thin planar layers and then join the layers together to form the final tablet. And each of this layer will have the drug distribution somewhat like this. So radially outwards, the concentration would decrease. And in every layer, while the drug is dispensed, its flow rate is controlled so as to get the desired concentration. Again, that was about sustained release. A second equally strategic application can actually be the multi-drug release, where we can actually have two different classes of drugs or two types of drugs which the patient needs to take in say quick succession into a single pill. And instead of giving multiple pills to patients who have to take them say multiple times a day, we can just give them one pill which can have both of these drugs, and they will get activated sequentially one after the other. So here is such an example where you have one pill embedded inside the other, and the release profiles are shown on the right here. So as we go along with time, maybe these are not of the sustained release type. They will have the usual release property, whereas initially the extent of release will be very high because of the higher surface area and the equal concentration. Whereas later, when the concentration remains the same, but the surface area has decreased, the percentage of drug release will fall down, or the rate of the drug release will fall down and eventually flatten out. However, we see that once the release of drug 2 terminates, the release of drug 1 terminates, the release of drug 2 starts, and that is because by this time we have already dissolved or eroded all of this outer surface. So now the surface of drug 2 is exposed, and now it can start getting released and sending the necessary drugs into the body. And then we have this release profile for drug 2. So again, in terms of the multi-drug release also, the binder-based powder bed AM process has proved pretty useful, and I guess this is already a commercialized technology. So apart from Professor Kapil's lectures, I have also prepared some content on this binder-based powder bed AM process, and most of it is from this review article which I have cited here. So it's by Mustafa et al. In 2021. It is published in the Progress in Material Sciences, which, as some of you might know, is a very publishes very authoritative reviews and complete reviews. So here is just a schematic of the binder jetting process, giving the details of the pre-processing, the printing process, and the post-processing. So initially, we have this print head which is depositing the binder or the ink, which is shown in yellow, onto the powder bed, and this is deposited in certain key regions to make the parts where we need them. Once it is done, there is a low temperature curing of the powder bed where the entire powder bed is cured at say temperatures of 200 degrees Celsius. to give some strength to the green part. Then this bed is depowdered and the cured parts are extracted. Once this is done, all the binder will be burnt off, and where there was binder previously, there will be voids remaining. These voids would actually lower the overall density of the parts, and this needs to be covered up. So that is achieved via infiltration by bronze or copper, and it is expected that whatever voids remained after the vaporization or burning away of the binder can be occupied this copper or bronze. So then they are lined up with this infiltration scheme, and again the entire assembly is sintered, this time at a higher temperature. And because of capillary action, the molten copper or the molten bronze will infiltrate. Our parts will not melt in this case, they will still remain solid, but copper or bronze will melt and infiltrate into the voids. And finally, we will remove the runners which were used for infiltration and obtain our final parts. Of course, we can clearly see that by in such a case, whatever be our intended structural material, say I wanted to print a material of steel, but even then I will have some extent of bronze or copper in it because of the infiltration step. And otherwise, the density of the part would be very low, say to the extent of some, say 50%, which is undesirable. This is perhaps a limitation. The paper also gave a very good comparison between the binder jetting based AM process and the laser powder bed fusion. Here are some of the salient points. So, as we discussed, binder jetting is compatible with virtually any powdered material, whereas the PBF is mostly suited for metal. And binder jetting actually has a very good potential or high chance to surpass PBF and can process the widest selection of materials among all of the AM processes. This is it. This is what gives binder jetting the industrial edge. Now, another advantage is that at least the printing process occurs at the room temperature only and under normal atmosphere. So we don't need any vacuum or the purging by any inert gases. You don't even need to close the chamber in some cases where the powder may not be otherwise harmful or dangerous. And there's issues which are common to other AM processes such as oxidation, the presence of residual stresses which leads to cracking and delamination, elemental segregation, and phase change are not encountered here. And this also means that the powder which remained loose and which was later recovered by means such as, say, pulling them through a vacuum are now highly recyclable. So their metallurgical properties and their mechanical properties, their structure, morphology is unaffected after the process, and it's as if they're as good as new. Again, because expensive sealed chambers for vacuum are not used, or because the chamber size can be fairly large, we know that even when you're purging gases, if the chamber size is very large, the gases will simply diffuse away, and we need to maintain very high flow rates. However, here, since neither we have to maintain vacuum or neither we have to purge the inert gases, the build volume can be quite large, and it can be among the largest among all the AM technologies. So up to some 2.2 meter into 1.2 meter into zero point 0.6 meter, while still maintaining the very high resolution afforded by inkjet. So we have both. We also have the large build volumes, which can print very large parts, as well as we also have the accuracy and the tolerance of very thin layers. This is perhaps not encountered in any of the other processes. And thus we can have the large size parts with highly complex features. We can have smaller production types, and the dimensional accuracy and defects can be greatly controlled. Again, in fusion-based processes such as laser powder bed fusion, the support material must be generated. Even though we have the loose powders which support the overhanging features, to prevent warpage of any overhanging parts, due to the presence of residual stresses, we must still have the explicit support structures, which then later need to be removed away. So this leads to both the consumption of excess materials as well as the requirement for post-processing steps. And even the removal of these support structures may leave some marks or will leave its signature on the final finished surface. Thus, resulted need also requires more time and more material. However, in binder jetting, it is a loose powder only which provides support since there are no fusion or there are no high thermal gradients and thermal cycling, there is no residual stresses, no warping, and thus no need for explicit support structures. Again, in other methods such as PBF, a heat source for melting the layers of powder is used, which leads to residual stresses in the final product. However, here we do have some heat input, say during converting the green part to a brown part and during curing the binder, later again during sintering. But during the build process itself, we don't have any high temperatures. The entire process is conducted at room temperature and pressure only. And thus, there is no significant heating or melting or phase change, which might lead to these residual stresses or geometric distortions. The rate of part production is also far higher compared to PVF processes where it is low because of the limitation of scanning speed. And also, as we discussed, the part itself can be of very large volume. There have been instances where certain designs or geometries with very fine features were found to be better suited for binder jetting. And as we were discussing, so it gives you the flexibility of processing FGMs based on composition by use of multi-materials or by changing the density or the gradient of parts. So various densities and control porosities in terms of shape and size are also achievable. However, it is also important to look at the drawbacks and limitations of the process. So some of the major drawbacks are listed here. First being that binder jetting is a multi-step process. It's not a fire and forget type of setup. So first we print the green parts, then we burn out the binder, producing a brown part. Then we sinter it to produce the final part. So it involves multiple steps and post-processing such as curing and densification and infiltration by a secondary material such as copper or bronze. The as printed part in their green state would have low relative density of 50%, which is, I mean, simply unacceptable unless you wish to produce a foam-like structure. And compared even to PBF, which has shown very high density, so at optimum parameters, it will be very close to 100%, some 99.5 plus. And once we start densifying the material from this state of 50% relative density, there might be some distortion of the geometry. The surface roughness and resolution, while good, are not really maybe as good as powder bed AM. And the post-processing strategies still need to be developed and optimized for most of the materials. I mean, one of the common drawbacks that we saw is irrespective of the structural material that I'm using to build my part, whether it is Inconel or steel or any titanium-based alloy, the infiltrating material would still be something common, like copper or bronze, which was not originally in part of my design and part of the material selection for this deposited part. Here are some of the major factors which affect the output of the process in terms of the final quality and properties of the built part. One is the morphology of the powder. This is something we have been looking at in all of the powder-based processes, which in fact determines the flow as well as the spreadability and the natural packing and packing density. By using the counter rotating or forward rotating roller or by changing the type of binder, we can change the density and the consistency of the green part. And historically and mostly the spherical particles have been used. Powder production using water atomization and attrition and milling are less expensive. And the powders generated via these routes will have also low sphericity and can also have a wide distribution in the sizes. The highly regular powders do not pack very well and may need, say, multiple passes of counter rotating rollers or some normal pressure, normal load along with it, and will have much less powder to powder contact. However, in terms of the printing process, the use of counter rotating rollers can mean that even such irregular powders can be shaped. Again, the size and distribution itself affect the flowability, density, and the powder binder interaction, as well as the layer thickness that can be achieved. So, of course, definitely, if you have powders of a coarser size, you cannot. The fundamentally limiting layer height would be the size of the largest powder particle, and often it is mostly 3 times larger than the mean particle size because of the wide distribution of the powder sizes. It can also affect the binder saturation and the final sinterability of the powder, where the thumb rule is that the fine powders will sinter faster. And generally, it is observed that smaller powders sinter better. However, larger powders pack better, and that is why we use a distribution of the powders to achieve both the best of both worlds. And the limiting size for powders which can be processed by a binder jetting has been stated to be 5 microns, and below powders of sizes below this are typically not used because of safety reasons. What these safety reasons are, we'll also look at in one of the upcoming slides. Again, the segregation of these powder particles can occur based on the size distribution. So it may very well happen that in one region you have very fine powders and in the other region you have coarser powders, and then definitely it is expected that the mechanical and metallurgical properties of the powders will not be the same. You will have some anisotropy in your deposited part, and it can occur in various steps of the process, such as during the feedstock preparation itself, or the feeding of this feedstock into the printer, or while spreading it using the roller or doctor blade. One needs to be aware of the influential factors on segregation, some of which are the material, the handling of the material, the operational and environmental parameters, and the powder must be remixed while filling into the reservoir. This is important to maintain the homogeneity. Also, some other additional means, such as oscillation of the hopper, followed by the roller compaction. The powder segregation may still occur in the build box area. Some efforts for the numerical modeling of the binder jetting additive manufacturing process have also been outlined in this paper. And here we'll discuss mostly the challenges of this. So the numerical modeling is still in its infancy, and the variety of challenges need to be tackled. First is, of course, the modeling of the powder spreading itself, and discrete element modeling. So DEM is discrete element modeling or discrete element method has widely been used to predict the powder spreading process and can also provide reasonable prediction after some benchmarking, as well as of the packing density and the surface roughness of the final powder beds. However, better understanding and more sophisticated models are still needed to capture the particle-particle interaction, such as if they grow rough or if there's some oxidation or electrical discharge involved. And these effects can actually change the surface material properties and thus the final part properties. The second aspect would be modeling of the binder powder interaction. For the current models, usually the dynamic wetting behavior have been focused on the planar surfaces. However, we know that the powder particles are very small and thus they have very small radii of curvature and consequently very high curvature. Whereas most of the modeling efforts have been focused on planar surfaces. Whether those theories of the planar surfaces apply to the high curvature powders is unclear. Again, the powder rearrangement and spattering driven by the binder impact is critical physics that affects the green part quality. So when we are actually dropping the binder droplets onto the powder bed, there will be some spattering, there will be some distribution, and how this affects the powder rearrangement is still unclear. And to have a faithful recreation of the process, these factors must also be taken into account. Thus, more comprehensive models are needed to incorporate the liquid-driven particle motion in the process simulations. And in terms of modeling the sintering process itself, usually phase field methods, yeah, it says the same phase field methods will give some very faithful recreations, and they are powerful to simulate the kinetics of powder densification, such as coarsening, diffusion, and others, and grain growth. However, it still needs greater thermodynamic consistency. And they also have mentioned the very specific factors which need to be improved, which are in this case the free energy density function and the model parameters should have more explicit physical meaning. They cannot simply remain mathematical constructs so that we can directly relate them to the actual material properties. And the debinding process is also an important step for the sintered microstructure, where the residual binder can introduce noticeable changes on the contact condition and the surface properties, which can in turn affect the densification kinetics to a very great extent. The debinding process can also be particularly important for the sintering of binder-rated green parts, which have a far higher volume to weight percentage of the binder compared to green parts. Now we discussed how the powder safety aspect is an important consideration in any powder-based additive manufacturing process, and that is because such powder materials have a very high surface area to volume ratio. This would be because we are very well aware that uh, nature will always try to achieve a state of minimum energy, and when the molten metal is uh, made into droplets by processes such as say water atomization or plasma atomization or gas atomization, and the metal droplets are simply allowed to move in free space. They take the inherently take the shape of spheres because for a given volume, a sphere will have the maximum surface area through which energy can be dissipated, and that is why naturally the powders take this shape. However, because of the very high surface area to volume ratio, they need extra attention because such characteristics can say prompt flammability and explosivity, and these must be thoroughly evaluated when you are working with such powders. And it's very interesting to know that even food grains can be combustible when in a cloud, and thus we need to have some explosivity safety standards which already exist in the food processing industries. However, AM has some additional challenges because of how the powders are emptied from the machines and how the powders are stored and reused, how they are handled, as well as for personal safety. So they are also breathing hazards and are may also be cancerous in nature if breathed in. Now, while binder jetting has traditionally used non-reactive metals and the equipment design reflects it, there is can also a shift to more reactive metals such as aluminum and titanium, which by the way are explosive in powder form. And whenever we are changing or shifting to more reactive metals, we should have a safety assessment of the equipment because primarily they are modeled or tuned to work with non-reactive materials. The facility protection as well as the personal protective equipment or PP should be properly looked after. And when we move to smaller particle sizes below 5 micron, these considerations need special attention. And we must prevent the formation of dust clouds, inhalation of the particles, as well as absorption via the skin. So even touching them is a hazard. And we must use proper gloves or personal protection equipments while handling such powders. The reactivity of powders is another concern to take note of, and metal powders have very high hazard potential due to the high burning temperature and the energy output upon combustion. Another very interesting feature is that a fact for all of us to know is that the solid rocket fuel is actually made from aluminum powder only. Each metal has a level of reactivity related to its composition, and powder metal has reactivity associated with the size distribution as well, apart from the composition. And when the powder is settled into a pile, when we move it or when it is in a cloud form, the reactivity potential will again change. Thus, there are certain testing and test standards which we can check for our safety. Some of them are listed here. One determines the combustibility, the other one determines the explosivity. So these are the contents which I intended to cover for this week. Let us take a short break and then we'll discuss some of the questions. So let us resume again at around 8:20.
Sir,
Oh, hi. Hi, I hear you. Please go on.
hi, sir. Sir, now can I ask a question, sir? Or after break, sir?
Yeah.
Can I ask
No, no, Karthi. Sure,
now?
sure. Please go ahead.
Sir, infield only copper and bronze only, both things only. Correct.
Yes.
Apart from the
Yes.
no infield.
No, so currently all the
Okay, sir.
literature
Okay.
that I encountered, they use copper and bronze only. I did not come across the example of any other metal.
It's breaking, sir.
Do you hear me fine?
Now fine, sir. Okay.
Yes.
Tell
So
me, sir.
what I said, yes, what I said is, so in all the literature that I have personally encountered, I only saw these two, bronze and copper. That might be because of the melting temperatures as well as the capillary action effects that these two metals exhibit. But I have not personally come across any other examples. So these are the two that I am aware of. Yes.
Okay, sir. Sir, another question.
Yes, yes.
In assignment number 11, assignment that means 11th week, the question is that is selective laser melting in us, sir. The orientation recoater blade, during a recoater blade, the parts, that means I am telling that in mass production, during
Okay.
mass production you have to keep the part slightly some angle, you have to keep in the SLM. Okay, say
Yes.
mass production, because in the
Yes, yes.
recoater blade will sticking strike hit the part, that's only they are keeping that parts as like some angle. But in that binder jet, so if you see that video, no sir, that video just copy and paste in the parallel to the rows, every rows.
Yes.
So
Yes.
here that recoater is never whether it is recoater blade will be hit or not, that is my question.
Okay. So I can tell you of a couple of reasons why the parts are aligned in that fashion for, say, the metal powder bed or electron beam powder bed. So one of the reasons, as you rightly mentioned, is the recoater blade can simply come in contact or collide with the parts. And to minimize the length that is in contact or supposedly in contact with the roller or the blade in each pass, we tilt them at an angle. The second reason can also be that you see those parts have to be separated from the build plate, and usually that will be achieved via the wire radium. And say we want to separate the parts, say one at a time, or we want to take out a certain section from the part. In that case, if all the parts are aligned parallelly, it will be very difficult because I would have to cut through all the parts at once. I cannot take the section out easily. Whereas if they're aligned at an angle, I can actually isolate the part I want to process and take a small section out. This is a problem which I have personally encountered. Whereas in this binder jetting, two things. First, there are no residual stresses, and thus there will be no warping of the parts. And thus the say probability of damage to the recoater or the roller is very low. Second thing is that even for separating the part from the powder bed, since it is not say explicitly connected to the substrate, we just have to take the loose powder out and we can simply remove the part by hand. So I think these are two reasons which I can think of the top of my head why the orientation guidelines for say powder bed fusion and this binder jetting are different.
Okay, sir. Um, sir, another my the suggestion is, sir, is sir our Patel sir during some videos now showing na sir, some videos showing and about how the operation is taking. That means, for example, in binder also, in SLM also, in the previous videos, if you see that one, some videos are showing by how the manufacturing and the saris some strike, that means go minimum, that means if for example the video is lengthy is 10 minutes means sir will see show that one only 5 or 2 minutes, because in order that much importance. But we need that video, sir, so separate, so whatever the sir is showing that video,
Okay, okay.
because due to the time consumption, so SAR is just minimum, that means reduce the time and showing that how the operation is taking. But we need that video, sir, because we want to see the total video. But in that Swayam, that the SAR will show
Yes,
only
yes.
for some videos, sir. After that he's go again come to the PPT. But we need that total video, sir. It is possible to upload in that in that say separate folder, or like anything, sir, possible.
Okay. So what I can do is I can request Professor Kapil to either upload the videos or at least he can provide the link to the videos, and
Correct,
using
sir.
that, yeah, you can access all of them. So I will request Professor Kapil, and okay, I expect a positive reply. So let's see. It might also be the case that the slides were prepared, say, a couple of years before, and some of the original sources are lost. But yeah, let us try and see if this can be done.
So what I'm telling you understand, sir?
Yes, yes, yes. I understand the videos that are shown in the slides. Sometimes he has to skip through them, show only the important parts. But it will help if
Yes,
the
sir.
entire video is available to the students.
Correct, sir. Correct, sir.
Yes, yes.
Okay.
So I will request him to share the original sources or the original videos.
Yes, sir. At least YouTube links, or a folder, separate folder in Swayam. Our means it is easy for us to see anytime, sir. That's
Yes, yes.
yes, sir. Yes. Thank you, sir. Thank.
Okay. Thank you, Karthik.
Okay. Okay. Sir.
So let us resume our session. So the first question is asking, why is the top feeding powder delivery system used in popular electron beam based powder bed AM? So is it to limit the chamber size? Is it to ensure that the vacuum is achieved in a reasonable amount of time? Is it because top powder delivery system inherently produces a more uniform powder layers? Let us examine each of these. So to limit the chamber size, so usually it has been found that when the AM machines are designed, so a bottom feeding one might have a larger size than a machine with top feeding, and it also might require more powder during the printing cycle. Even if the amount of or the part we are printing is smaller, still, since we need the loose powder over the entire print area, the overall volume of powder which we'll be using, eventually recovering though, would still be pretty large. So yes, it has been found that the top feeding systems do lead to more compact designs of the additive machine. Second, since the chamber size would be smaller because of the use of these top feeding powder systems, the amount or the volume of air inside would also be smaller, and thus the vacuum can be achieved in a reasonable amount of time. If we have a very large build chamber, because of whatsoever reason, whether it is because of the use of the bottom powder feeder or whether it is to ensure that we can print larger parts. If the chamber size is very large, the amount of or the volume of air inside would also be very large, and then it will take a really long amount of time to achieve vacuum. And we have already discussed why uh, achieving vacuum inside an electron beam based AM process is very important. First, it is electrons are very light particles, and in EBM, the melting or sintering takes place when these electrons transfer their kinetic energy to the powder feedstock. Thus, if there are any other molecules or heavier molecules, such as those of air present in the chamber, the electrons will simply collide with these molecules and get dispersed. And thus, they would be unable to transfer their kinetic energy to the powder feedstock. This is the reason for necessity of vacuum in the build chamber. A far higher degree of vacuum is also required in the gun chamber itself because there the filament is exposed to very high temperatures. The presence of any other particles can lead to oxidation, maybe even combustion, and thus the filament will fail prematurely with a very short life. Thus, the to ensure that vacuum is achieved in a reasonable time, the top feeding delivery nozzle or the delivery system can definitely help by limiting the chamber size. However, there is no research which shows that the top powder delivery system will inherently produce more uniform layers. The uniformity of the layers is more a function of the recoating system than the powder delivery system itself, and thus this cannot be said definitively. Thus, both A and B are the correct options. The second question asks, why are regular spherical shaped powders preferred for electron beam based powder bed AM? Is it because the spherical powders have improved flowability? Is it because they tend to produce a uniform layer thickness after recoating? Or is it because they are easier and more economical to produce? So spherical powders definitely have more improved flowability compared to, say, powders with a more acicular structure. So these won't really be as flowable as, say, uniformly circular powders. Second, so option A is correct. Second, the spherical powders tend to produce a uniform layer of thickness after recoating. This is true. However, to ensure this, we must have a distribution of the powder particle sizes. So, in terms of the frequency or the number and the size of the particle, say the diameter, excuse me. We will never have just, say, particles of one size. What we'll always end up is with a distribution, and it is this entire distribution range that we utilize. Of course, it will have some mean particle size, but we need this entire distribution because to ensure good compaction and say a uniform layer height, just having particles of one size won't do. We also need smaller particles to fill in these regions, as well as in certain regions we need larger particles, and thus a synergistic combination of all of these will produce a uniform powder layer. However, to ensure the high degree of sphericity of the powders, the quality control and the processing has to be very rigorous, and thus they are costly to produce. They are definitely not very economical, and neither are the processes very easy. So this option is incorrect. Thus, both option A and B are suitable. The third question is asking why is the scanning beam speed in an electron beam based powder bed AM system up to 3 orders of magnitude higher than in laser based systems? So, if you would remember, when we were discussing the electron beam based powder bed additive manufacturing technologies last week, we read how the scanning speeds in some of the EBM based setups can be as high as 10,000 meter per second. Whereas in laser based systems, these would typically be of the order of 10 meters per second or even lower in most cases. But what is the reason for this high speed performance? Is it because the galvanometer has low but significant inertia, whereas there is no inertia in EV based systems? Is it because the galvanometer mirrors are rotated using mirrors? Or I guess this is motors, whereas in EV based systems, electromagnetic coils deflect the electron beams dynamically. Is it because the EV based powder bed AM is a more advanced and recent technology compared to laser based AM systems? So let us examine all of these three reasons. The galvanometer is actually the deflecting mechanism, which is basically a mirrors connected to motors, which are used to deflect the laser beam all over the printing area in laser-based systems. So the galvanometer does have very low inertia, and thus it can be deflected rapidly. However, the inertia is still significant. It might be very low, but it is finite and significant. However, in EV-based systems, there is no inertia at all that we are dealing with. The particles, electrons, are some of the lightest particles known, and there is no mechanical inertia as such, which we have to overcome. So option A is definitely true. The galvanometer mirrors are rotated using motors, whereas in EV-based systems, the electromagnetic coils can deflect the electron beam dynamically as well as almost instantaneously. And EV-based powder bed AM is a more advanced and recent technology. So if we remember correctly, EV-based AM, powder bed AM, came before SLS and SLM. So it's not the case that this is more recent. Yes, in recent years it has been garnering more attention and continues to be an active area of research. But inherently, that does not provide it any advantage in terms of the quicker scanning speeds. So both options A and B are correct. The fourth question says a student proposes the idea of blown powder directed energy deposition using an electron beam as the energy source. What advantage will this technology provide over the laser-based blown powder directed energy deposition? Will it have a lower cost of operation? Will it give us higher production speeds? Will the lower porosity of the finished parts be an advantage, or is it none of the above? Let us examine these reasons. Will it have a lower cost? Well, that depends on a multitude of reasons and cannot be judged so objectively. Both the laser based and electron beam based systems have their own advantages and drawbacks, and economics of scale. The production speeds in the electron beam based system can be higher because, as we discussed, at least in the same plane, the scanning speeds can be up to 3 orders of magnitude higher for the electron beam based systems. So, this might be true. The finished parts have a lower porosity, but it has been observed that with modern laser based and electron beam based technologies, very high densities up to the order of say 99.8 or 9% can be achieved in either of the processes. However, a quick examination of all the options, or in fact of the question itself, tells us that the idea is of blown powder directed energy deposition using the electron beam as the energy source. We have discussed how it's very important to maintain vacuum in an electron beam based additive manufacturing setup because of the requirement of vacuum in the build chamber as well as the requirement of vacuum in the gun chamber also. The moment we use some carrier gas to blow the powder into the deposition zone, this vacuum will be terminated and violated. Thus, it simply is not compatible, and thus, this technology is simply not possible. Thus, none of the above advantages can be had. The next question is asking, why do binder-based powder bed AM processes typically have no atmospheric control? Is it because of the low process temperatures? Is it because of the low to none chance of oxidation of the powder particles? Is it because the addition of a vacuum system will increase the machine and the process cost? So let us examine all of these options in great detail. So we discussed how in binder jet based AM processes, there is no fusion of the powders involved. We deposit a binder selectively, and this binder makes the powder particles stick together, which leads to the production of a green part. This green part will ideally have sufficient strength so that it can be handled and post-processed via the binder burnout and sintering to produce the final part. Since the process temperatures encountered are very low, thus the need for a closed cabinet or a closed chamber can be foregone, and thus the atmospheric control is not really needed. Also because of the low temperatures, the feedstock material will not get easily oxidized. Again, there is no oxidation because of these reasons as we discussed. And the addition of vacuum system will increase the machine and process cost. While this is true, this is not a reason for foregoing the vacuum system because so what's needed is needed. But in this case, it is not required at all. Thus, both options A and B are correct. Question 6 is asking, what are the advantages of binder jetting over other additive manufacturing processes? And some of them are listed here. So is it that in binder jetting we encounter no residual stresses? Is it that in binder jetting there is no need for the support structures? Is it that in binder jetting there is no need for any environmental control either? Or can a wide variety of materials be processed by binder jetting? So let us examine these options. Of course, like we were just discussing, no residual stresses are encountered in binder jetting processes because there is no fusion, no phase change from solid to liquid and then back, no thermal cycling, and thus no residual stresses involved. Consequently, there is no requirement for support structures because A, the loose powder particles themselves are acting as the support structures to support any overhanging parts. This was also seen in the laser powder bed fusion. However, there, because of the residual stresses, the distortion of the part geometry was still encountered. And to overcome that distortion, the regions, especially the overhanging regions, still needed explicit support structures to connect them to the substrate and to keep them restrained. However, here the loose powder particles themselves act as the support structures, and because of the absence of the residual stresses, there is no chance of any warpage, and there's no distortion, so no explicit support structures are required. Similarly, as we discussed in the last question, there is no need for any environmental control either. Because the process temperatures are low, there is very low chance of, say, oxidation or any corrosion or any chemical thermally induced reaction, and neither do we need a vacuum. Thus, the environmental control is not needed. And as we have definitely come across in the slides, a very large variety of materials, and typically all the engineering materials, such as polymers, metals, ceramics, and a combination of any of these, can be processed via binder jetting to produce functionally graded materials. Thus, all of the above, that is, all 1, 2, 3, and 4, are suitable. So, those are the questions which I had for this week. I really feel fortunate to have been a part of this NPTEL course on the fundamentals of additive manufacturing technologies. It was a great learning experience for me as well, both while going through the videos and slides of Professor Kapil, as well as while interacting with some of the participants of this course. And I really look forward to similar opportunities in the future. For now, there is nobody in the meeting, but I'll still keep it open for some time in case somebody joins and there are some questions raised. So this was week 12 of the live sessions for Fundamentals of Additive Manufacturing Technologies. I am Sourav Goswami from IIT Bombay, and thank you very much for attending all of the sessions. I look forward to interacting with all of you in the future as well. Thank you. Thanks a lot.